the outcome of the last handful of lectures was that we can really use a layered architecture to make our robots act like a simpler system, like x dot equal to u in our case. And the key idea was to plan using the simple dynamics and then track using some clever controller. And what we saw last time was we could use a PID regulator, for instance, for controlling the heading of the robot, and then simply set the velocity of the robot equal to the magnitude of the planned velocity, u. Well, today I want to discuss another twist to this theme. In fact, I want to be even more clever. And there is a particularly elegant and cute way you can think about unicycles. And in general, I'm not a big fan of clever tricks for the sake of clever tricks. But because differential drive mobile robots are so common, and we know that unicycles model them well, then this trick becomes more than just a piece of mathematical curiosity. It becomes an effective way of thinking about a large and rich class of mobile robots. So instead of doing tracking, we're going to transform the unicycle dynamics. So recall that we have the position, xy, we have the heading, phi, and we have the dynamics as seen here. Well, typically, what we've seen so far is we want the robot not to slam into things. We want the robot to end up on top of goal points. We want the robot to follow walls. We don't particularly care which way it's pointing. So the first thing we're going to do is say, you know what? Let's just pretend that we don't worry about orientation whatsoever. Well, we still have a rather awkward-looking nonlinear differential equation, but let's now pick another point. Let's not pick xy, which, as you remember, was really the point right in between the wheels of the differential drive mobile robot. What if we picked another point instead? Let's pick this point, the red point here, and let's say that the distance between the red point and the black point, there's some distance L, where L is some small number. What would happen if we looked at this new point instead? Well, let's place the new point at x tilde y tilde. Then x tilde is simply x plus L cosine phi, simple geometry. And y tilde is y plus L sine phi, where again L is the distance we're moving our point along the heading of the robot. Well, let's see what the dynamics of this new point, the tilde point, actually looks like. Well, this is our old dynamics. This is how x and y and theta actually behaves. This is our new point. Now, what we need to do is put dots over the tildes to see what do the time derivatives actually look like. Well, it's not so complicated. X tilde dot, well, it's x dot plus the time derivative of this thing, and the time derivative of cosine phi, and remember, phi is a function of t. If I take d dt of this thing, then what I get is I get minus phi dot times sine phi. Well, that's what we have here. X tilde dot is x dot minus L phi dot sine phi, and similarly for y tilde dot. Okay, this still doesn't seem all that helpful, to be completely honest, so let's simplify this a little bit. Well, first of all, I know what x dot is. It's this thing here, so instead of that, I'm just plugging in v cosine phi. I also know what phi dot is. It's omega, so now I end up with a slightly less scary-looking expression. And then we do the same thing for y tilde dot. Well, okay, where does this lead us? Well, let's assume for a second that we can control this new point directly, that this new point is indeed the point that we before have called x dot equal to u as a way of generating reference velocities. Let's assume that we can actually immediately control this new point. What would that tell us? Well, x tilde dot, as you recall, was given by this mouthful of an expression. Well, let's set this equal to u1, which is our desired velocity in the x direction. And similarly, we set y tilde dot equal to u2. Now, all we need to do, at least I can say all we need to do, I don't know if we can do it, but all we would like to do is actually solve this equation with respect to v and omega, because if we did that, we would relate the actual velocities of the unicycle to these u1 and u2 velocities, which are the planned velocities. So let's see if we can do that. Well, the first thing we do is we pull out the cosine and the sine terms. So we get that cosine times v minus sine times L omega, well, that's that thing, that's equal to u1. And similarly for the y tilde dot, or the u2 dot, sorry, the u2 equation. Okay, I don't know, this equation still looks a little hairy, but as you hopefully recall, this matrix right here is a rather nice matrix. It is, in fact, a rotation matrix. All it's doing is it's taking a vector and rotating it theta degrees. Actually, it's rotating it phi degrees, but it is a very well-behaved and well-understood matrix. Okay, I don't particularly like L there, because L is not part of what I would like. I would like V and omega and no L. So what I can do is I can rewrite this thing as a matrix, a diagonal matrix, with 1 on the first diagonal and L on the second diagonal, simply times V and omega. And if I do that, I get the following expression. Rotation matrix, phi, times this matrix, V omega. Well, these are all invertible. What is the inverse of the rotation matrix? Well, the rotation matrix rotates something phi degrees. Well, the inverse would be to rotate it back, right? Then you're back where you started. That's minus phi. So our inverse phi always exists, and it corresponds to rotating it back phi degrees. So we can invert this matrix easily. Well, this is a diagonal matrix, and the inverse of this thing is simply the inverse of the diagonal. 1 over 1, 0, 0, 1 over L. So the inverse of this thing is also trivial. That means that I can actually solve directly for V and omega, no problems. No questions asked, no tracking, no approximation, just bam, I get the right velocities out. So if I have my low-level plan producing u1 and u2, then I can transform that into V and omega directly. And this seems almost too good to be true. And it is too good to be true, because remember, we're actually not making x, y behave perfectly. We're making this new point that we called x tilde, y tilde. We're making that point behave perfectly. And then we have L that tells us how far away we are. And by making L small, we're getting closer to x and y. So in practice, you pick L tiny, and then you go to work. So what does this mean? It means that before we had a planner, we used our complicated navigation algorithm to spit out u1 and u2, right? And then we had a tracker, and in our case, we used a PID tracker for the heading and simply set the velocity equal to the magnitude of u. And from that, we got V and omega out. Well, now we don't have to deal with trackers. We've actually replaced the second part with a transformation of the unicycle, where we're simply saying that V and omega are these two matrices times u1, u2. And again, these matrices are not particularly complicated to compute. This is simply the rotation matrix, and phi, of course, we have. This is 1, easy to compute, it's just 1. And L is something that we decide. So what we put here, this is 1 over L. L should be small, so 1 over L should be some large number, right? And the larger this number becomes, the closer the tilde point and the actual point approach each other. I should put out a little warning, though, that if you make this number too large, then you get a behavior where the robot starts turning quite a bit, because this is going to hit omega directly. But this gives us a direct transformation instead of a tracker to produce the desired velocities. And the reason why I like this trick and why this trick shouldn't be thought of as simply an interesting little curiosity, because it is kind of interesting, is that so many robots are differential drive robots. And this transformation applies to all of them. because all of them can be mapped onto the unicycle dynamics. So that takes care of how do we actually go from low-level plans to executable desired velocities for differential drive mobile robots.